Thank you, everybody, for joining us today. We're going to start our webinar presentation. This is our first introductory webinar on our data portal, so we're very happy to have you. I'm Kenzie Huffman, Director of Strategy and Partnerships, and some of you might be familiar with Carbon Mapper, but for those who aren't, we are a nonprofit organization focused on helping to drive emissions reductions by making methane and carbon dioxide data actionable and accessible. We use remote sensing technology to detect, pinpoint, and quantify methane emissions and CO2 point sources at the scale of individual facilities and make that data available via our public data portal. To deliver on this mission, we also lead the Carbon Mapper Coalition, a unique public-private partnership powered by philanthropy to develop and deploy satellites that will help routinely detect, monitor, and quantify major emitting sources. The Coalition's first satellite, Tanager-1, launched this summer. The satellite was developed by Planet Labs with technology from NASA's Jet Propulsion Laboratory. Ultimately, our goal is to scale to provide sustained monitoring of up to 90% of methane and carbon dioxide superemitters globally. That said, we also know data alone isn't enough to drive reductions. We need more tools and capacity to turn this data into action. Our goal today is to give an introduction on the type of emissions data we provide and give an overview of our data portal's key features and functionality. On today's webinar, Dr. Dan Cusworth, Carbon Mapper's Director of Science, will provide an overview of why we are focused on point sources, also known as superemitters, a bit about the technology and methods we use, and how the data can be applied. Then Alex Diamond, Carbon Mapper's Director of Products and Engineering, will provide a walkthrough of key features of the data portal. We'll have time for about 10 to 15 minutes of Q&A at the end. We'll be using the Q&A feature in the Zoom webinar. There should be an icon at the bottom of your screen. Please submit your questions there throughout the presentations, and then I will be moderating questions with our panelists or with our presenters at the end of the presentations. If you have questions on that, please add to the chat. This is the first webinar of a series we are planning to host to help provide more sector and user-specific guidance on the data. Our next webinar will focus on using the data to better understand waste sector emissions, so much more to come, and we'll definitely want to keep you all apprised as we get deeper into the webinar series. So with that, I'll hand it over to Dr. Dan Cusworth. Dan?
Thank you so much. And I'm going to go ahead and share my screen. Hopefully you can all see. Is that the case? We good? All right, so it's really a pleasure to be able to speak to you today about Carbon Mapper and our data portal. And here's just the folks who will be talking to you today. Kenzie already spoke to you, our Director of Strategy and Partnerships. I'm Dan Cusworth, the Science Director at Carbon Mapper. And in a minute, you'll hear from Alex Diamond, who's our Director of Products and Engineering, who will do a walkthrough on our data portal. But really, it's my pleasure today to give a little bit of a scientific background on what types of data Carbon Mapper is providing and really what are the main scientific questions we're addressing. So in order to do that, I just want to take a step back for a minute and maybe do a little bit of level setting with regards to definitions and where we find ourselves with respect to methane emissions. And to do that, I want to define this key feature, which is how do emissions manifest in many places globally, especially in anthropogenic sectors, so like oil and gas, waste, and agriculture. And in these sectors, there's this differentiation. And of course, emissions are very complex and dynamic, but you can think of it in terms of two broad categories. And one of them is an area source, and the other is a point source, or an area source and a super emitter. And what this basically means is that, first, just look at this figure we have on the bottom right. You see this oil and gas basin, lots of dense infrastructure. Each of those pieces of infrastructure where there's gas extraction may have some sort of emission, right? As you're pulling oil out of the ground, there might be some fugitive emission, or as you're storing it in a tank or moving it in a pipeline, small seams here and there can lead to small emissions. In aggregate, across all of that infrastructure, it makes up an area source, right? The total flux, the total emission that might be coming from that basin. But what's really key, and what we found repeatedly over multiple surveys, is there's this other feature called super emitters or just point sources. And what these are disproportionately large emission sources that might occur in a basin. And so you can think of these as being leaks, malfunctions, or they could be the result of maintenance, a maintenance emission. Someone needs to work on a pipe, so they have to release some gas, or they have to vent some gas. And why these are important is that these point sources or these super emitters can be quite disproportionate in terms of the total emission contribution that may be made up in a basin. And so in this cartoon, we have an area source estimate making up about half of the emissions, while the point sources make up another half. And so this is really key because the point sources represent a very small fraction of total infrastructure that might exist in a basin, but they can be quite disproportionate in terms of their total emissions. So with that in mind, with that definition, we really want to get to why are we addressing methane and why are we addressing methane super emitters? So methane itself is a much more powerful greenhouse gas than carbon dioxide. In fact, probably 86 times worse over a 20-year time scale. It's also short-lived in the atmosphere, meaning that if we reduce methane emissions, we can actually see the climate benefit of that within our lifetimes. And so if we're trying by 2030, by 2050 to reduce emissions so that we can keep atmospheric temperatures and global temperatures stable to stave off the worst effects of global warming, methane really represents an avenue to do this. And in particular, these super emitters can be quite effective at reducing the methane emissions if we target them because of those facts that I brought up before, which is a small number, a small fraction of infrastructure, maybe 1%, 2% of all infrastructure in a basin can make up 20 to 60% of all the emissions in a basin. And it cuts across multiple sectors like oil and gas and waste and agriculture. So by focusing on those super emitters, that's a real near-term climate benefit we get. Obviously, we have to address the whole system and we have to address CO2, but if we're thinking near-term reductions, super emitters can be a very effective way to reduce our global burden of greenhouse gases. And so that's what we're focusing on today and in this presentation, and that's really what the Carbon Mapper data portal is designed to bring insights against these super emitters. And when we talk about that, we have to think about, well, okay, so what are super emitters? Why are they important? So the question is, what types of observations do you need in order to address it? And so what we have here is a picture of a global distribution of fossil fuel methane emissions. And what you can see from this figure is that they occur all over, right? It's not just the US, Europe, it's every continent has fossil fuel emissions and fossil fuel methane emissions. So you need a global strategy that can do a few things in order to reduce and to bring data to this global problem. And one of it is a global monitoring solution. So bringing observations everywhere globally in a sustained fashion so that we can get data across countries, across economic regions. You also need to do it with high frequency. Methane emissions can be quite variable. They can be quite intermittent within a basin. Like I said before, there might be some persistent sources. So there's a leak, so it's lasting from days to weeks. But really, there's a large fraction, if not, potentially at least half or the majority of the methane emissions that may only last for a day to 2 days to 5 days. But when you take all of those short-lived events together, they can still be quite large in terms of the total impact on climate. So you need to have a monitoring solution that has regular revisit as well. And you need to have it that is highly sensitive. So you need a monitoring solution and observations that can get down to an emission detection limit that is sensitive to kind of the full range of super emitters. And when we talk about super emitters, really we mean anything that's in excess of 100 kilograms an hour of methane. So that's the kind of the three axes of what type of monitoring solution you need. You need spatial coverage, revisit, with high sensitivity. And again, that's where we're focused here with Carbon Mapper. That's where we're moving towards with our technology and our portal to be able to track this system. Okay, so now I want to get a quick, this will be very quick, and there's lots of literature on it, but how does the technology work? What we use here to basically design that type of observing system is built on the foundations of imaging spectroscopy. And really, we have a simplified diagram here, as you can imagine. Solar radiation comes from the sun, goes down to the earth. Some of it's backscattered, some of it's reflected off the surface of the earth, and then it goes up to a satellite. And the principle of solar backscattered radiation and methane is that if you have molecules of methane or a greenhouse gas that are inside of this path from the sun to your satellite sensor, the absorption features of methane, the methane molecule itself, is such that you can actually detect a elevated concentration of methane, presuming those molecules exist within this light path from the sun up to the sensor. And so it's this principle of absorption of greenhouse gases that makes their observation possible through imaging spectroscopy. Maybe another diagram that shows how this is done in practice is this one here. We have a satellite that is scanning the Earth. So you imagine this picture on the bottom. Imagine that satellite's moving in that flight direction. And as it scans the Earth, it observes solar backscattered radiation, not just in the visible spectrum, which is, what your iPhone does or your camera does, is looks at the red, green, and blue channels. It's looking at a lot of different wavelengths. So that includes the near infrared as well as the shortwave infrared. And in the shortwave infrared, methane and carbon dioxide are very strong absorbers of solar backscattered radiation. So as the satellite is moving across this path and it is measuring what's happening at those shortwave infrared wavelengths, if it detects an anomaly in terms of absorption, that can be translated to a methane concentration and actually to a methane plume. So this box is a detection that we were able to acquire from imaging a source on the ground and using that shortwave infrared reflective properties or shortwave infrared absorption properties of methane. Just as a quick caveat, of course, this type of observation, since it relies on sunlight, means that it's going to be limited in some situations where the observing conditions are not ideal. And so this can be in situations of cloud cover. It can only work when there's sunlight, so we can't see at night. We can't see in the winter in the Arctic where there's no sunlight. It can only work well when you have reflective surfaces. So if you have a really dark surface, of course, it's going to be impacted because there's not as much sun being reflected back to the sensor. And then this last point is wind speed. And this actually depends not on the spectroscopy, but on just the atmospheric dynamics. If you have a plume that is, in an environment with extremely high wind speeds, that plume, that methane concentration might get washed out very quick. And so it's no longer detectable. But by and large, these are factors that influence the detection, but the principles are such that we have a generally reliable way to quantify and pinpoint large methane emissions when we use the general principles of imaging spectroscopy. And here at Carbon Mapper, we use several types of technology that range from aircraft to satellite. And so what you'll see on our portal today are plumes, methane plumes that we've detected using the AVARIS NG, the Airborne Visible Infrared Imaging Spectrometer, next generation, the Global Airborne Observatory, and then AVARIS 3, which is kind of the next generation. Again, these are airborne imaging spectrometers. They are sensitive to solar backscattered radiation in these shortwave infrared wavelengths. There's a very similarly built instrument, satellite instrument, that's on the International Space Station called EMIT, that we also process data against. Now, what you can imagine is that each of these sensors has a slightly different configuration in terms of what its signal is compared to the noise of the instrument, and then also how it's deployed. So an aircraft, it's closer to the surface, it's more sensitive, its spatial resolution is much better, meaning that it has a lower detection limit. When you go to something like EMIT, this is on the ISS, it has a much larger spatial resolution, spatial footprint. And that, in addition to the noise properties of the instrument, means that you have a higher detection limit. So for the airborne, we're pretty reliably able to detect emissions down to about 45 kilograms an hour. When you go to the EMIT platform, it's 1,000 kilograms an hour. Now, this third satellite, which we're really excited about, which we just launched in partnership as part of the Carbon Mapper Coalition and in partnership with Planet Labs, is the Tanager satellite, which has an improved spatial resolution. It has a lot more signal in that shortwave infrared region where that's where we do our methane detection. And thus it has this anticipated detection limit that's actually quite a bit lower than what we're able to do with EMIT. And so that data should be coming soon in the next year. Here's just a quick example of, once we make the raw measurement of absorption features from methane, what do we do to it? And so there's a quality control protocol and also an algorithmic protocol where we take raw concentration imagery that we derive from the spectrometer. An analyst will look at it, compare it with simultaneously acquired visible imagery that comes from the red, green, and blue channels of that spectrometer, as well as other base maps. They'll make a determination of the origin of that plume. That then sets off a series of segmentation, so how you mask the plume from the background, and also emission rate quantification processes, so that you can get with a data product, you not only get in an elevated region of methane concentration, you get a attributed origin point, and you get an emission rate with quantified uncertainties. There's another principle that Alex will go into in a minute, which gets to this question of persistence. And like I said, some methane emission sources are quite variable and they're quite intermittent. So we have this term that's called persistent, meaning that if you have a single emission source, and we've observed it multiple times, we may have observed plumes on some overpasses, and then in other overpasses, we may not see anything. But what we do on our portal is we say, well, let's try to take the characteristics and the dynamics of the plume over a time period to try to constrain total emissions, meaning a detection, a non-detection, and a detection, again, we will create a metric called persistence, which is the number of detections divided by the total number of observations. And we use that when we quantify what the total impact of emissions from that source is. So when you're looking at the portal, like I said, this really cuts across all anthropogenic sectors, and it also is a global. So you will see emissions that are coming from oil and gas, from coal, from agriculture, from LNG, onshore and offshore. All of these sectors, in a global sense, we have seen evidence of super emissions. And this is the types of data sets that you can anticipate to grow with additional observing that we're doing at Carbon Mapper. And then I kind of want to wrap up where I say, we've had a lot of experience working, not just providing data onto a portal, but actually taking that data and working with stakeholders, working with interested parties to be able to translate into workflows and processes that are very important for said stakeholders. And we have a few of them listed here of these various use cases that these types of data sets can enable. So, leak detection and repair, best practices, differentiating gas supply chains, policy, trending, air quality. These are all functions that are enabled and that we have examples of enabling that by working with stakeholders across regions and across the spectrum. So more data here to learn more. I am going to hand it off now to Alex to actually show you the portal, show you how to use it, and happy to take any questions if you put them in the chat and answer them. So thanks so much.
Hi, everyone. I'm Alex Diamond, Director of Products and Engineering here at Carbon Mapper. Hopefully everybody can see my screen. So here we have our data portal. And now that we've explored this broader context of Carbon Mapper's mission and methodology, let's just dive into the public face of our platform. What you see here is our data portal. So this tool provides simplified access to high-resolution methane and carbon dioxide data, enabling users to visualize and analyze emissions across various sectors and regions. During this segment, I'll walk you through the portal's key features, show you how to search, filter, and explore the data, from viewing individual sources to understanding regional point source emission trends. So let's start out and take a look at the portal's overall layout. What you see here is the global map view. And if I start in the upper right, you'll see that we've detected 17,379 plumes to date, with a total of 6,418 sources. Moving over to the left side here, you can see our search box. I'll go ahead and clear out my previous search. You can search here by location name. So you can search for California, Los Angeles. You can search by lat long coordinate or plume ID or plume name. We also have the ability to draw or upload an area of interest with these drawing tools, or by uploading a geospatial file like a zip shape file, a GeoJSON, or a GeoPackage. On the left side here, we have our My Account, Save Search, and Download buttons. And on the bottom, we have our Summary Statistics, Accessibility Toggle, and Settings tools. So I'm going to come back to all of these in a few minutes, but the first thing I wanted to show is our Sources panel. So this is our Sources overview. It allows you to kind of scroll through an infinite list of all of the global sources worldwide. I can sort this by the acquisition date, the published date of the particular plume, or by the emission rate. But what I'm going to do now is just dive into one of these particular sources. So we'll go ahead and search for location in Iran. This is a gas processing facility. So the search updates as we sort of zoom and pan around the map. But you can see this plume here, and I'm going to go ahead and open our layers dialog. So with this layers option, I have the ability to change the base map. So I can change it to a satellite view to help you kind of see features on the ground and the context around the plume, or I can set it back to our default base map. I also have the ability to change the opacity. So here I can change the opacity. If I do that along with the satellite view, you get a better sense of the context around the particular plume detection. I also have the ability to turn on some overlays. So I'm going to go ahead and turn down the opacity, and I'll first turn on our gas overlay. This is interesting because this is basically useful for viewing the raw methane data, showing the concentrations within the plume above the background levels. And this image here is what the plume image is actually derived from, and you can see how it lines up. And you can see the higher concentrations here near the origin, spanning out to some of the lower concentrations downwind. I'll go ahead and turn off that overlay, and I can turn on the what we call the RGB layer. The RGB layer is really just a natural color image that's collected simultaneously with the methane detection. And this is useful for being able to compare the ground features alongside the enhancement and really trying to get a sense for, what might be happening on the ground during the moment that we capture the methane detection. So if I turn that off, I can take a look at our coverage layer. So to do this, I'm going to zoom out a little bit. So we'll go ahead and close this view and zoom out. Let me turn back on the default base map, just a little easier to see. This shows our coverage, basically where we have collected data with the various sensors that we use. Describe this in a little bit more detail later, but let me just zoom into California here. You can see some of the different sizes. So each instrument that we use is represented by a distinct shape. Some of the larger boxes are the satellite observations from the EMIT sensor. The smaller boxes are these airborne observations. And these distinct shapes really indicate that each detection method has its unique detection threshold. And that threshold really impacts the coverage and completeness that we have globally. So again, I'll come back to the coverage layer in a little bit. Turning that off, we also have this other tool here, just basically a tool where you can turn on and off the clusters. So right now, these are just clustering all the global sources, but if I wanted to see all the individual sources, I can just turn on and off this cluster point. So that is a useful tool there. So let's go ahead and bring back up our location that we were looking at earlier. Go ahead and zoom into that using some of our search features here. And the last thing I wanted to show is a measuring tool. So this measuring tool right here can be used to measure sort of from the origin of the plume out. And this is really useful for measuring the distance between the plume and a facility that would be maybe classified as like a sensitive receptor, like a population or a school. So you can see approximately from the origin here to maybe more of a populated town is about 1.82 kilometers away. And that's a good use case for this measuring tool. Okay, so let's go ahead and turn off the base map again. We'll close the source detail view and we'll zoom back to the global overview. And I'm just going to walk you through some of our search capabilities here. So we talked a little bit about searching by location name, lat long coordinate, or a plume ID, but we have a lot of filters that are usable here as well. So first things first, spatiotemporal filters like date range. So I can filter emissions by observation period. If I wanted to look at like 2019, 2021, or any time range that you choose. We have our sector filters. So if you want to choose different sectors, here I'm selecting oil and gas and solid waste. You can see that the search results update as I do that. Go back to default, which is all. You also have the ability to select the instrument. So we're adding new instruments over time, hopefully coming soon here. We have the Planet Tanager, but we also have some of our legacy instruments as well as NASA's EMIT instrument. And moving further down here, we have the ability, obviously, to select the gas type. So whether you want carbon dioxide or methane, or you can turn one on and one off. You can see that the different sources have different colors on the map. Also have the ability to change the emission units. This is really cool. Our default is kilograms per hour in methane or carbon dioxide, but we also have the ability to choose like carbon dioxide equivalent using 100-year global warming potential, or carbon dioxide equivalent with 20-year global warming potential. And you can see the values here changing on the right. Finally, we also have the ability to list the units in thousands of cubic feet per day. And this is a thousands of cubic feet per day in gas. And this is a more common unit used in the energy industry. So go back and change this back to the default. And we also have these filters, these filter ranges. So I can change the source emission rate, set this to say 1,000. So the source emission rate, this is basically the mean emission rate of all the plumes associated with the source. So all the plumes clustered around a particular source, which again is like a facility on the ground that emits plumes. So this is the mean emission rate of all those plumes associated with the source multiplied by persistence. We'll talk about persistence in a little bit here, but this rate applies to the source overall, not just the individual plumes. So other than source emission rate, we have the ability to adjust the number of plumes. So if I wanted to see sources with more observations, I can make that adjustment here. I've set it to 10. And then I have the ability to adjust source persistence. So persistence, is Dan touched on this. This is a kind of a key metric. This is the frequency at which a point source emits. And we define it as the number of plumes detected divided by the total number of overpasses. So if we flew over a source 10 times and we observe methane 5 out of those 10 times, that would be 50% persistent. So if I adjust this to 50% persistent, you can see as I'm adjusting these filters, the number of sources on the screen changes, and it gets updated here in the upper right. Okay, last filter to show is what we call our plume cluster distance. This is a handy filter. Basically, this is the minimum distance that plumes must be from each other to be considered in the same cluster. And again, a cluster are these basically is a source. So the minimum distance plumes would have to be from each other to be considered as part of the same source. So our default plume cluster distance is 500 meters for the solid waste sector. And for all other sectors, it's 250 meters. Okay, so as I adjust all these filters, it creates what we call these breadcrumbs or little evidence of the sectors that we've chosen. Not just the sectors, but basically any search criteria gets stored up here in the top bar. And I'm able then to save a search and save that to my account. Assuming I've registered and I've logged in, I can save a search and then come back to it. And I'll show you how that's useful here right now. So go ahead and close that, clear out my filters, and zoom back to the map view. Then I'll go to my saved searches, and I'm going to go ahead and zoom into this livestock facility in California. So I'm going to go ahead and clear the area of interest, and we'll just zoom to the source. So this is a source with lots of different observations, and I think it's a good use case to kind of show what we call our source detail panel, or source detail view. First thing you can do here is I have a handy little link to open this same location in Google Maps. So as I bring up Google Maps here, you can see the location of the source and get a better sense, or a different set of satellite imagery to sort of see what's happening on the ground. Coming back to the data portal, I can expand this top section here, and I can see the source name. So this is a name that you can actually search in the search. Copy this and search in the search box. So the convention here is basically the gas, the sector using some IPCC codes, and the cluster distance, which I mentioned before, 250 meters, and then the lat long. So that is what comprises our source ID. Sector is livestock, gas type is CH4, methane, and I'll go ahead and describe some of the figures you see here. So some of the headline numbers that we have at the top, once again, the source emission rate, which is the mean emission rate of all these plumes associated with the source, and then we multiply that by persistence. So take the mean of all these plumes, multiply that times 53%, and you get a source emission rate of 200 kilograms per hour. The total number of plumes you see here are 29 plumes across 19 days of observations. More plumes and observations. So you can see on the chart here, we have some detections all happening on the same day. So the y-axis is kilograms per hour, and the x-axis is date. Okay, so let's move down into each individual plume. So as I click on a particular plume, you can see that it recenters to the origin of that particular plume, which is associated with this source at this livestock facility. It's indicated by this plume origin point, this orange point, whereas the spinning purple point is the source point. So the plume is associated with that source. You can see here in the plume details, we have the acquisition date and time, and the plume emission rate. So this is the emission rate for this particular plume. We also have, it's copyable, the plume name. So you can search based on that particular plume name, or the lat long. We also have the sector, the instrument, platform, and then we have the acquisition date again, the date that we published it to the portal. That's kind of a key date. And then we have the wind estimate. So the wind is a critical component for calculating the emission rate. And you can see here that the wind is 1.9 meters per second, and it's from 342 degrees. So if you think sort of in a circle clockwise, 342 degrees would be coming out of the northwest. So I'll go ahead and close this particular plume. And I want to introduce a concept here that we have called null detects. So if I go ahead and toggle on this option, what this does is it turns on null detects. So null detects are indications of where emissions were below the threshold of the instrument that we use to observe a particular source. It doesn't necessarily confirm the absence of an emission. It just shows that we didn't detect anything at this particular source on that particular date and time. And it's important to note that we only log these null detections for sources with prior plume observations. So toggling this on and off, you can see that the total number of observations increases to 40, still over 19 days observed. And then we get these no plume detected observations. And basically you have the scene name and the lat long, but since there's no plume detected, there's no additional information there. A couple other things to show in the source detail. We also have some supporting details just for the source, total number of observations, how many came from airborne, how many came from satellite, the days detected and the days observed. This is how we calculate persistence. So you take 10 divided by 19, and that's how you get the 53%. Number of plumes, number of null detects, sector, source emission rate. Some of this is repeating from what you see on the main tab, but some of these supporting details can be helpful. Okay, last thing to show here, you have the ability to share. So I can copy the URL and you can share that with a colleague. You can also just copy directly from the address bar. You can download from here. So if you wanted to download all the plumes and plume images at this source, you can either click the CSV option or the TIFFs option or both, and then you can download basically a zip file that contains the plume emissions and the plume images. And then finally, you have this comment report feature. So if you happen to know something about the specific source or this plume, or you just want to drop us a line, you can do that here. Just include your message, your email, and the topic that you wanted to tell us about. That's all possible from this dialog. So I'll go ahead and close that. See that lots of questions coming in. Hopefully everybody's following along okay. I think we'll take more of the questions toward the end here. So for now, I'm going to go ahead and clear this source, zoom back to the overview, the global view, clear the search filters. And I wanted to show a feature we call summary statistics. So summary statistics is an interesting sort of experimental feature. I can go ahead and turn this on. And what this is doing is summarizing the key statistics of emissions across the sectors that have been observed, or basically it works in conjunction with our search filters. So if I have no filter selected here right now, what it's doing is summing up basically all the point source emissions that you see in the view or that you've selected using your filters. So it's the sum of all individual point source emission rates in the field of view in kilograms per hour. This is helpful for just sort of trying to calculate I guess what you might call it like a point source emissions inventory for the data that you see on the screen. So here we have 2.1 million kilograms per hour, along with our uncertainty. So I think I probably should have touched on this before. The uncertainty is important. Every time that we measure a emission rate or a source emission rate, we include the uncertainty, and the uncertainty range shows the reliability of the measurements. So since methane emissions can vary due to environmental factors or detection limits, this uncertainty range ultimately reflects the confidence in the data. So really important. I'm glad I caught that. I didn't mention it before. You can also see it here in the source detail view. We're always going to report an uncertainty. Okay, let's jump back to summary statistics again. Bring that back up. As you can see, as I zoom back out, this is updating. If I zoom in a little bit here, just over, say, the continental US or North America, it updates again. You can see the majority of emissions here are coming from oil and gas sector. I can choose solid waste, or I can choose livestock, and you can see the share of emissions in that field of view. What's interesting here is you can also use this in conjunction with areas of interest. So if I wanted to, I have this feature where I can search for a location, and I have the ability to just zoom to that location or to use it as an area of interest. So you can see on the map here, I search for California and it creates an area of interest for me. And it's now going to constrain all of these point source emissions by that area of interest. So now 48,700 kilograms per hour, and you can see the share of emissions. I also have the ability to upload a file. So if I search for the Permian, my desktop here, I think I have a GeoJSON. Similar to searching for a location, I can simply upload a file, and it acts as my area of interest. I can also go ahead and close that. I can constrain this by date too. So let's just say 01/01/2019, and we'll do 12/31/2019. This is now going to basically update along with the total data point source emissions just for that time range. Okay, so we'll go ahead and close that out and clear our filters. Just a couple more things to show here, and then we'll get to our question and answer session. Close out summary statistics, zoom back to the whole world. A couple of other things to show. So we have here on the left our downloads options. So this is really helpful because it allows users to export lots of the data, or all the data that you see here, different types of data, and use it in your own GIS systems or your own emissions management systems, and do further analysis and combine it with data that we might not have on hand. So if you wanted to download all the sources, 6,418 sources, you can do that here. It'll download a GIS format, GeoJSON. If I wanted to download only the filtered sources in my view, I have that ability as well. If I want to download plumes instead of sources, I have that option. Just note, with plumes, they have a max of 1,000 plumes that can be downloaded at any time. So you'll want to use your filters, constrain it by area of interest or by date, or any of the other filters to get it below that 1,000 plume limit. Same thing for scenes. So I showed you that coverage option before. Those are our scenes. You can download scenes here in various GIS formats. And that is also limited to 1,000 at a time. There are ways to exceed that using our APIs, but if you're doing it from the portal, you'll want to use those filters. Finally, we have this bulk downloads option. So if you wanted to download our plumes CSVs that contain all of our emissions, and along with the plume geotiffs, or just the CSVs without the geotiffs, we have these categorized by year here. We usually update these about once a quarter. If you need more recent data than that, you'll want to just download directly from like our plume download option here. Okay, so that's our downloads. I'm going to come back to the coverage layer just for a second here. So I don't think I showed this before, but if I zoom into a dense area, I'll go ahead and turn the clusters back on. I can click at any location, and I can get a list of all the active scenes at that location. So if you're trying to understand, how many times has a location been observed and what the dates were, you have that capability here. You can see all the individual dates. You can see the number of satellite observations, number of airborne observations. This can be done really anywhere. I have also the option of turning it on the ID of the scene, and then you can search based on that, or you can just look at the date as well. So that's our global coverage option. And once again, yeah, the different sensors have different shapes, and that reflects in different detection thresholds. So it's really important to kind of understand how that all works together in terms of our coverage and completeness. Okay, so last couple things I want to show, I think, is just a few options down here. We have an accessibility toggle. So if you want to engage with the portal using features like this high contrast mode, or if you wanted to use keyboard navigation, this accessibility feature is helpful for those that might have a little bit trouble seeing things in the normal mode. Okay, so we'll go ahead and close this. We'll toggle accessibility off. Last thing here is our settings toggle. So we have a how to use it capability. This brings up a guide that'll kind of walk you through some of the things that I already walked through today. Using search, navigating sources, viewing source details. So that option is there for a little self-education on how to use it. Definitely encourage you to take a look at our product guide. So this is a PDF document that provides an overview of the products that make up our data platform. So it includes a detailed description of each Carbon Mapper product, along with product uses, generation time, release latency, data format. It's a large document. Definitely take advantage of looking through it and understanding, our data and our how we develop our products and all the information associated with that. Last couple things here, we have a link to our API endpoints. We'll probably do another webinar sometime in the future that dives more into our APIs, but you can click through some of the most common endpoints that we have here and how you can access our data and work with it programmatically. Just be aware that for using the API and some of our download capabilities, you do have to register for an account first. So really simple to do. You can just do it right here in the portal. Once you register for an account, you can get tokens for the APIs and and other ways of basically using the data programmatically. Last thing to show here is our FAQ page. So along with the product guide, this links to our FAQs on our website. Lots of good information here in general about Carbon Mapper and methane and CO2 emissions, and some more information on our data, like, how do you define a plume in a source? How do you define persistence? Is this real-time data? Lots of good information here. So I think that's about it for now. It looks like we probably still have some time for questions. So I'm going to go ahead and turn it back over to Kenzie for Q&A.
Thanks, Alex. Thanks, everybody. It is a very exciting, we have a lot of questions. So we probably will not get to everyone's question, but what we will do is try to summarize and share some responses either in the live chat or following up the webinar, just because there's so many and they're all great questions. So with that, I'll try to also pull some of them together so that we're hopefully hitting multiple questions with one answer. And so with that, I think we've gotten a number of different questions around data coverage and kind of what the cadence of data from all the different sources is on our data portal. So, like when are EMIT observations available, when are Tanager observations available, things like that. Alex, would you be able to kick us off on kind of this question of cadence and then also data coverage? And then we can get a little bit more into specifics with other pieces.
Yeah, I'm trying to see the specific question, but in general, cadence, different sensors collect data at different frequencies. We try to process the data quickly. Our goal, especially with the new Tanager constellation, would be to collect data and process it within 72 hours for methane quick look. And then when we publish the data, the data gets published from all of our sensors once we go through our QC process. That's anywhere from about a week to 2 weeks. With Tanager, I think that data comes out at 30 days. So that's a specific time frame just for the Tanager data. And I'm sorry, Kenzie, what was the other question? I'm not sure I addressed that correctly on frequency.
Oh, good. There was too many pieces. The question was, can you talk a little bit about data coverage? So someone asked what might be missing from the all up point source inventory. And I think this could, it would be helpful to talk a little bit about kind of what our plans are. And Dan, this was also be great for you to talk through of kind of where observations will populate and at what cadence.
Yeah, maybe I'll just jump in here. And there are a lot of similar questions. So just to clarify a little bit, the airborne campaigns, we fly those where we can, right? Where we have access to fly them and where it's possible. So you'll see a lot of coverage in the United States over major oil and gas basins and over landfills. Those aren't, those we try to do them routine, but a lot of the data are one-offs, et cetera, but they've been very useful in establishing baselines. EMIT is on the International Space Station and it points nadir. So it has no control over tasking or orbit. It just, when there's an opportunity to collect some data, it will collect it. And we process that for emissions. Tanager is a tasked instrument. And so we can task that globally. And going back to what I showed previously in the talk is that we are very interested in building this observing system that addresses the question of super emitters to task the major sectors where we anticipate there to be large super emitter activity that cuts across all sectors from oil and gas, agriculture, waste, coal. So as we increase the data with Tanager, you will see kind of coverage of all of those regions. And as that constellation grows, the revisit of those regions will also grow, which will improve things, as people have also put in the chat, like creating annualized emission at a source level, because we'll have more constraints on the variability and the intermittency of those sources.
Thanks, Dan. And then there, another question for you is, there have been a couple of questions around uncertainty and how that's calculated, and how we account for null measurements in that calculation.
Yeah, so just generally speaking, and lots of questions on, algorithms, I think in general. So, maybe just, trying to do this a little bit quickly, but first off, on retrievals, we use a variety of retrieval methods, primarily being matched filters, but we also run radiative transfer based retrievals as well. For validation of emission rates or calibration in general, the instruments are calibrated radiometrically in the lab and on orbit. And this is for radiance to make sure you're getting the right radiance numbers at the right wavelengths. And then we do additional validation on the emission rates. And this is through controlled release experiments, aircraft underflights, simultaneous observations with mass balance approaches as well. And so we try to build this deck of emission rates that we use for validation of our algorithms. In terms of uncertainties, the uncertainty on an emission rate is decomposed into several factors, which includes the retrieval itself, that concentration retrieval, the plume segmentation approach that we used, the wind speed, and the length of the plume, how we estimate the length of the plume. So all of those get added into our uncertainty budget. We have that in our algorithm theoretical basis documents, which are to be published very shortly that people can look at, which goes through that whole process. Null measurements, we just take those into account in that persistence calculation. So it's like averaging as a zero, so to speak, as if there were no detection. We're working towards bringing into the various detection limits of the various sensors on our platforms into a more holistic uncertainty where it comes to persistence. So that's something to stay tuned for as we roll that out.
Excellent. And just one kind of in that spirit of summary, we have gotten a number of different questions around impact and engagement with other organizations. So one big thing is we do have a big resource on our website around some of our case studies of where we've worked with states and others to take the data to drive action. And that has given some kind of comprehensive insights around when data is shared with operators or regulators. Actually, we've seen about 50% of what we've identified has actually been voluntarily addressed, and these are all based in the US. And so one of the things that we are actively looking to do and grow is to partner with other organizations to help do more of that work. So there were some different questions about different applications around the data for, being used in kind of legal context or others. And I think that's really where our focus is in providing this data, grounding it in the science, and then working with decision makers, regulators, operators, and others to take the data to drive action. And so there's a lot more work to do, and we're really excited to partner. So if you are interested in partnering with us, please do reach out, and we'll provide an email address on that at the end as well. So with that, I think there have also been a number of questions about, Alex, some functionality with the data portal. Some questions about, are folks able to download the column concentrations, or is that not available? And I'm going to dig into other questions in a sec.
Yeah, we do offer two types of plume images that you can download directly from the portal. So I think I showed in that source detail view, you have the option to download. It will download both our color map, turbo color map plume image that shows concentrations in parts per million per meter just on a color map. But we also include a geotiff concentrations file that includes the actual parts per million meter concentrations within each pixel. So you have the ability to do that from the portal itself at using each source detail download. And then you can also download concentrations either in the form of this is why it's good to look at that product guide. We have our level 2 atmospheric retrievals. Those rasters can be downloaded, and you can examine the concentrations there. Or we also have some stack collections that represent our concentrations. So if you know how to use a stack API, or if you want to reach out, we can help you basically learn how to download that data programmatically. We have some tutorials on our public GitHub page, public platform GitHub page. So you could check out Carbon Mapper at GitHub and see some of the tutorials that we have there for Stack.
Awesome, thank you. And then there've been some other questions on other emissions. And so Dan, can you talk a little bit about the CO2 application and that we have that on our portal as well?
Yeah, right. This has been very, methane focused, but we can also detect with this type of spectrometer CO2 plumes from stationary point sources. And, really it's mostly limited to those types of sources because they produce a plume, right? A very concentrated plume. And so this has been very useful for us to bring carbon dioxide data for many parts of the world where there are large power plant emissions, but there aren't great inventory estimates, or there are inventory estimates that conflict with one another in terms of the total emissions. And so helping provide data on this can, reduce the uncertainties in that sector, but also, any quantification of CO2 from large point sources. So this could be, exceptionally large flares from gas processing plants. We've shown that we're in some of those cases, we've been able to do CO2 quantification. For other sectors like transportation, again, you're kind of in that point versus area source. So a little bit of CO2 from a lot of cars, that becomes a distributed area source. And so it becomes more difficult to do that type of quantification with this class of spectrometer.
And then we've also gotten a couple of questions on offshore and LNG applications, if you could speak to that as well.
Yeah, absolutely. One really exciting thing about Tanager is its ability to look off nadir in such a way that, we can see glint, and glint is the specular, really shiny reflection off the Earth's surface or off of water surface. And this is really exciting because it enables the possibility of doing a methane plume detection and quantification from offshore platforms. Traditionally, it's very difficult to make that measurement with solar backscatter because, like I said, you need the photons, you need backscattered radiation, and in the shortwave infrared, water just absorbs it all. So usually you don't get a signal. But if you have that glint opportunity, you can get a signal. And we've prototyped this with aircraft. You can see it on our portal that in the Gulf of Mexico, we've seen many offshore plumes by showcasing this glint ability. So of course, this is also high on our list to do as Tanager moves forward, is to get a global baseline of offshore basins by employing this glint observing mode. And we're also very keenly aware of LNG, and that actually goes back to the CO2, is we've published papers and have been looked at quite a bit of CO2 emissions that come from liquefaction plants, as well as any methane emissions that may come from fugitives. And so we're in the process of acquiring more observations so we can do more of a synthesis analysis on it. But certainly that's something to be expecting as we move forward with observations.
Thanks so much. And I know we are nearly at time, so I'm going to wrap up, but we are planning to share the recording of this webinar with all of you who attended, as well as amplify it for those who could not join us today. And then we will follow up with some answers to questions. But if you have any additional questions or interested in partnering or want to learn more, please email us at info@carbonmapper.org. And we'll work to get you a response or connect you to a partner at Carbon Mapper. But thank you all so much for joining us. I also mentioned this at the start, but this is the beginning of a webinar series to help provide more tools and resources for users to better understand the data and our data portal. And the next one will be focused on the waste sector and waste sector emissions. So please be on the lookout for that. And we hope to continue to see you and engage with you. Thanks, everybody.